Hi, so today we're going to be talking about the vector or cross product. So earlier we know that the dot product of two vectors gives us a scalar, which is just a constant, and it was taken like this, where you multiply the components accordingly, and then you add them up to get a scalar. So today we're going to be talking about the other product that we need to know for vectors, which is the cross product. So the cross product denoted by A cross B, and if we have two vectors a1, a2, a3, and b equals b1, b2, b3, we find the cross product by taking the determinant of this 3 by 3 matrix that we can set up. So we start off by writing I, j, and k are our three basis vectors in 3D space, and then the components of a, so horizontally like this, a1, a2, a3, then the same for b, b1, b2, b3. Don't worry too much if you don't know how to take a 3 by 3 determinant, because you can either just learn it now or you could remember the formula. So essentially, this is how you take it. You take the component, block these two, and take the determinant of the remaining 2 by 2 matrix, and you do the same for all the other vectors. So for j, it'll be like this, and then k, it'll be like this. But note that our j is minus. This is just how it works. I'm sorry, I can't tell you why in this video, but yeah. So this would give us a2 b3 minus a3 b2 I minus a1 b3 minus a3 b1 j. Then let me shift this over, plus a1 b2 plus minus a2 b1 k. So this is our cross product. Our cross product. So you can write this in a column vector like this. Um, I like in our basis vectors I use the minus, but in column vectors you can just switch the sign. It's just minus. It comes out to be plus. You know. So it's a sorry a3b1 minus a1b3, and finally a1b2 minus a2b1. So this is our cross product, or the vector product for two vectors. And so notice that this gives us a vector instead of a scalar like our dot products. So that's an important thing. Similarly to the dot product, we can write this using trigonometry. So it's a bit different because this is a vector, so we need a unit vector to define this vector. So we have a cross b is equal to the magnitude of a times the magnitude of b times sine of theta, the angle between them. Notice this is sine instead of cosine like the dot product, and some normal vector, which is a vector that's mutually orthogonal to both a and b. That just means for two vectors a and b, it is perpendicular to both of them, so 90 degrees and 90 degrees. And that is also where our right hand rule comes from. So you can search for a picture online of the right hand rule. And so this is our vector form, and if we want the magnitude of our cross product, we just get the same thing but without our normal vector, because it's the magnitude. This is a scalar. All right, so that's our cross products. One thing we have to notice is that orientation matters. So multiplication works a little different. For dot products, remember, a dot b was the same thing as b dot a because it was just multiplication of numbers. But here, due to how the determinant works, a cross b is negative b cross a. So what does this mean geometrically? Well, if we have two vectors a and b, our cross product gives this vector a cross b, and if you do b cross a, you will get a vector with a opposite direction. So yeah, you'll get a different direction. So Um, if you do the right hand rule, you will see that this is in fact true. And now we can look at some properties of some more properties of this operation. So, for example, we already had this one. This is important, and we also have the distributive property over addition. If these are all vectors, this gives us A cross B plus A cross C. And scalar multiplication works similarly to dot products, where this is equal to the constant or the scalar multiplied by the cross products of both vectors, because it really applies on both things. So, what are some applications of the cross products? So, in physics, it's actually used widely. So, for my dear physics students, you remember in A4 we had torque, which is the turning force, or the, you know, the the force applied to give a turning effect. It's defined as r cross f, where r is the distance of the axis from the point where the force is applied. So if we have some rod and we apply some force f like this, this distance would be r and this force would be f. So of course we can represent both of these things as vectors. So yeah, this is just an example of what the cross product can do for us in real life or in physics. The cross products is r cross f. This is torque, and this is also how we get our formula for the magnitude of torque. In our syllabus, we only need the magnitude of torque. It is just r f sine theta. So that's how that formula comes. And yeah, I hope this video helped.